So let's take a look at this car example here. We have a sports car that has a mass of 2 megagrams, and engine efficiency given to us is epsilon is equal to 0.65. Moving forward, the wind creates a drag resistance on the car given to us by F sub D is equal to 1.2 V squared N. So this is going to be relative to the velocity of the car. So V is the velocity in meters per second. The car is going to accelerate at 5 meters per second square starting from rest. So they give us a lot of information. It starts from rest. We know our initial velocity is 0. It has an acceleration of 5 meters per second squared. It has a drag force given by this relationship relative to our velocity. We have an engine efficiency, and we have a mass of the car. They want us to find the engine's input power when our time is equal to 4 seconds. So our plan of attack for this problem, 4 different steps here. First, we're going to start off the same way as before and draw a free body diagram of the car. Next, we'll apply the equation of motion and the kinematic equations in order to determine the car's velocity at a time of 4 seconds. Third, we'll determine the power required for this motion. And fourth, we'll use the engine efficiency to determine the input power. Now that we've had an opportunity to go through the problem statement, understand what they've given us in the wording, as well as the initial diagram, we can now write out our first setup page here. So on our setup page, we have a simplified version of our diagram. There's our car with a velocity v moving off the left side direction here. Givens, we know our mass is equal to 2 mg, megagrams, it's a capital M. Our efficiency, our epsilon, is equal to 0.65. Our drag force is given to us by the relationship F sub D is equal to 1.2 V squared in units of newtons. Our acceleration is equal to 5 meters per second squared, and our time is at 4 seconds. Now they want us to find the input power when time is equal to 4 seconds. We'll call that variable there a P sub I for our input power. Solution, first step from our plan of attack that we saw within our problem statement there was to develop a free body diagram. Now on our free body diagram, we want a coordinate system here. So we can see our positive y is going up, positive x going to the left over here. So let's take a look. There's our car. Going in our negative x direction, we have our drag force, opposing the direction of motion here. We have a force of the car going with, so this is why we chose this to go in the direction of motion of our car here, our positive x, so positive F sub c there. We have our normal force on the road pushing back up on the car, and we have our weight here of 19.62 kilonewtons. So we can take our mass and gravity in order to get our weight force there. So, thing to note, our frictional force between the wheels and the road pushes the car forward. So that frictional force is what's going to propel the car forward. So from our frictional force there, we have our N sub c and our F sub c that represent the results of the forces on all 4 wheels. So our frictional force and our normal force there are going to compose that. So what we can do, take a look at this diagram down the bottom here. There's our wheel rotating, direction of rotation there. Our friction opposes the direction of motion. So this is our frictional force, our F sub c, right here, opposing the direction of motion of the wheel. But to propel the car forward, the wheel rotates there. So the wheel's direction tangent to that point of contact on the ground is going back in our negative x direction. So our frictional force F sub c, propelling the car forward, is right there going in this direction, our positive x direction. So now let's keep up our free body diagram and our coordinate system right here so we can reference back as we move to the next part of our solution, which is to come up with our equations of motion. Now, every time we've done equations of motion, what we want to do is separate things out in terms of their individual directions and components. So we're just going to look at our x components in our x direction right now. So we redraw our coordinate system here. So in our positive x direction, we're going to do out Newton's second law for our equations of motion. Summation of forces in the x direction is equal to mass times acceleration in the x direction, where our mass is going to be 2,000 kilograms. So remember, it gave us in megagrams. We need to convert to kilograms here. And our a sub x, acceleration in the x direction, is given in the problem statement as 5 meters per second squared. So we have our right-hand side of our equation from Newton's second law that we can plug in for our summation of forces to get our equation of motion. So now what we want to do is concentrate on this part of the equation here, summation of forces in our x direction. So what forces are acting in our x direction? Well, that's where having a free body diagram right there to reference back to is very helpful. We look back up here and say, okay, we're not worried about these two. These are in the y direction. So we're only concerned with our x direction here. So we have a frictional force from the car here, F sub c, and we have our drag force here, F sub d. F sub d is going in the negative x direction. F sub c is moving in the positive direction. Right there, F sub d we know is 1.2 v squared. So we can say F sub c minus our F sub d of 1.2 v squared is equal to max, where m is our 2,000 kilograms. Our a sub x is given to us as 5 meters per second squared. Plug those in. Our only unknowns are F sub c and our v. So now we have one equation and two unknowns. F sub c is equal to 10,000 plus 1.2 times v squared in units of newtons. So now that we have this relationship here for our F sub c involving our velocity, so if F sub c is equal to 10,000 plus 1.2 times v squared, units of newtons here, we look and we notice, okay, I don't know my F sub c and I don't know my v, my velocity here. So two unknowns, one equation. So in this case here, we need another relationship or equation to relate our velocity. So where we're going to pull these from is for kinematic relationships. So we take a look and we realize we have a constant acceleration. So we're going to take a look at our constant acceleration equations. When we do that, we see we have this one here. Our v sub x is equal to v sub x naught plus a sub xt. This is perfect. We know we have a time given to us in the problem statement. We have a constant acceleration given to us, an initial velocity of initial condition at time 0 as well. So the only unknown is our v sub x, so we can solve directly for v sub x. So v sub x is equal to our initial velocity, for it starts from rest, so our initial velocity is 0. Our constant acceleration is given to us as 5 meters per second squared, and our time is given to us as 4 seconds. So from that there, plug and chug, we end up with v sub x, our velocity in the x direction, is equal to 20 meters per second. So from this here, we know we can go back up to this relationship here, from our summation of forces from Newton's second law, and plug back in for our velocity in order to get our F sub c. So we know that. The next thing we want to figure out is, okay, what did they ask us to solve for? Well, they asked us to solve for the input power. So if we recall our relationship here, our epsilon, or our efficiency, is equal to our power output divided by our power input. So if we calculate our power output, we can rearrange this and say that our power input is equal to our power output divided by our efficiency, and they gave us our efficiency in the problem statement. So let's take a step backwards and look for our power output. So power is equal to force times velocity. So in the x direction, we have our power output is equal to F sub c times our v sub x. Now we have a value, 20 meters per second for our v sub x. We can plug right there, and we can get our F sub c from this relationship here by plugging in our v sub x right there. So we have power output is equal to 10,000 plus 1.2 times our v sub x from right here, 20 squared, times our v sub x of 20 right there. Plug those in. Our only unknown is our power output, so power output is equal to 209.6 in units of kilowatts. So we can take this value now for our power output, go back up to our efficiency relationship rearranged, and we see that our power input is equal to our power output divided by efficiency. So our power input is equal to 209.6 divided by 0.65, our efficiency. Therefore, that gives us our power input is equal to 322 kilowatts.